In 1851, Léon Foucault successfully demonstrated the rotation of the Earth using a 67-meter-long pendulum in Paris's Panthéon. Over several hours, the plane of oscillation precessed noticeably around the vertical axis, an effect roughly explained by the pendulum's plane being fixed and the Earth moving beneath it. Using the local Cartesian coordinates x, y, and z on the Earth's surface, the system is governed by some very complicated coupled differential equations, which can nonetheless be solved using numerical methods. Assuming small displacements and neglecting the centrifugal force, they reduce to a much simpler set of equations with an analytical solution for x and y, describing the pendulum oscillating with the expected period and the oscillatory plane rotating or precessing at a uniform rate K dependent on the Earth's angular velocity and the co-latitude of the pendulum's location. From here on out, we'll only focus on the pendulum's position in the xy plane. To get the full picture, we can solve the more complicated equations using the ODE45 routine in MATLAB, with an initial displacement of 3 meters in the positive x direction and no initial velocity. What we get largely resembles the analytical result, but with a couple of noticeable differences. For one, the period of precession is slightly longer, by about an hour, and additionally, the position of equilibrium is shifted a bit in the positive x direction. Let's take a look at the centrifugal force. This isn't a real force, but a fictitious one observed in rotating reference frames, such as the surface of the Earth, and it's defined by a cross product. On Earth, it points outwards, parallel to the equatorial plane, and with the strength varying with co-latitude. If a stationary pendulum is set up at an arbitrary location on Earth, the bob of the pendulum will therefore appear to have three forces acting on it in the Earth's reference frame: its weight, the tension in the rod, and centrifugal force. In equilibrium, the x component of the centrifugal force offsets the bob by a very small but still calculable distance by resolving the forces. For the 67-meter-long Foucault pendulum, the offset of the co-latitude of Paris is about 0.115 meters. And this lines up strikingly with the offset observed in the numerical solution. In the formula for the offset, it doesn't depend on the initial displacement of the pendulum, so we should see the same offset for a different displacement. We can try it with 0.5 meters, and we'd see the same offset, although now it's much more noticeable. So what about the precession period? Well, knowing that the equilibrium is offset, we can calculate the angle turned through by the pendulum in the xy plane about this new equilibrium over one period, and compare it to that predicted in the analytical solution to try to get some insights. Plotting the predicted angle, given by kt, where t is time, minus the actual angle theta, we see that this difference d does not grow uniformly as we might expect, but appears to initially be flat, then grow at an increasing rate, then grow at a decreasing rate, level out, grow increasingly, grow decreasingly, and level out again. At the times where the graph levels out, the derivative of the difference is equal to 0, meaning that the actual angular velocity is equal to the predicted angular velocity. This matches when the oscillations are occurring mostly in the x direction. At the times where the growth switches from increasing to decreasing and vice versa, the second derivative is equal to 0. This matches where the oscillations are occurring mostly in the y direction, and in the x direction as before. We can thus conclude that the precession initially slows down, then speeds up, then slows down, then speeds up again over one precession period. One potential explanation for this lies with the equilibrium position being offset, but the point of suspension of the pendulum remaining at the origin of the xy plane. The centrifugal force, acting in the x direction, can produce a torque on the pendulum bob in the xy plane about the origin, given as a cross product of the position vector and force. This implies that the torque is 0 when the oscillations are occurring in the x direction, as the force and displacement vectors are aligned, and maximized whenever they are occurring in the y direction. However, when the oscillations are occurring in the y direction, the torque on one side of the oscillation is balanced by the torque on the other side, so there's no net torque and there's no net angular acceleration. When the plane of oscillation is in other orientations, there's a net torque, and so the precession is either sped up or slowed down. This concurs with the results we observed, and also explains why the precession rate seems to catch up after each half precession. Finally, the Foucault pendulum fails to make complete precessions for larger initial displacements. The animation on screen shows what happens if an initial displacement of 15 meters in the x direction is chosen. We see that the pendulum initially precesses clockwise as expected, but then slows and reaches a maximum of about 30 degrees before reversing direction and reaching the same angle in the opposite direction, then reversing direction again. This could lie with the torque being greater due to the greater distances from the origin, or perhaps some other effect to do with large angle pendulum behavior in general. So, in conclusion, we have used the mechanics of the centrifugal force to try to explain two departures of the numerical solution of the small-angle Foucault pendulum from the analytical solution. The offset of the x-equilibrium was successfully predicted by analyzing the forces acting on the pendulum when it's in equilibrium. And a seemingly plausible explanation of the increased period was given based on the uneven torque created by the centrifugal force in the xy plane. We also took a brief look at larger angle behavior, which showed that the pendulum failed to fully precess at all.